something, we've actually talked about it. It's just that I didn't call it potential energy, and some of you probably guessed. We've already talked about potential energy when it comes to springs. We're also going to start talking about potential energy when it comes to gravity. The equation that we use when we're talking about potential energy due to gravity is even easier than the spring one. The spring one wasn't super complicated. The biggest issue with that is the units, because if you don't make all your measurements in meters, seconds, kilograms, then you end up being off by some factor of 10. But with gravity and looking at gravitational potential energy, the equation is even more simple. There's less to it. But conceptually, it's a little bit more difficult. When you look at a spring, it's really easy to see where the pushing and pulling is, what the work would be, and where ultimately the energy is stored. With gravity, it's a little bit different, so we have to play some mind games to really get the idea of gravity. So the goals for today is for you to be able to relate the work that we did last week to the idea of something called elastic potential energy, and then to be able to calculate that and calculate gravitational potential energy. And then we want to talk about work as it occurs in a gravitational field, which is a little weird. There's some weirdness to it because if you drop something and it just is in free fall, then everything makes sense. It's moving down, it's accelerating down, the force is down, and everything makes perfect sense. But as soon as you start looking at something where things aren't moving straight down, like if you have something on a ramp, like a tilted ramp like this, or a series of curved ramps, like our skateboarder in the simulation yesterday, it becomes more difficult because it turns out that for relatively easy to explain reasons, doesn't really matter. The ramps don't matter at all. The only things they end up doing is changing the direction of things. And so, so that we'll play around with a little bit today, and you're gonna have some work to do with that. And then we'll think about what kinds of predictions we can make due to that work. So if the force of gravity is doing work to something, work is the process of speeding something up. So if work is being done, something should speed up in some predictable way. So can we make those predictions? And you will be able to. Okay, so let's just jump back to springs for a second. So we talked about the idea that springs can do work. If we squish it a certain distance, then if it pushes on something, as it expands, it will exert a force on that thing, and there will be a distance over which that force is applied in the direction of the object's motion. Work is force times distance, so strings can do work. That works whether they're stretched and they pull on things, or squished and they push on things. And it was a little tricky because the force isn't always the same. So if you squish a spring and it pushes until it's unsprung, then it's not pushing with the same force the whole time. Starts pushing with a large force, it ends up pushing with no force whatsoever. But because that force is linear with respect to the distance of the spring, we were able to kind of piece together this equation here, which says that if we know the spring constant of a spring, how much force there is per unit of squish or stretch, and we know how much it's stretched or squished, then the amount of work it can do if it pushes on something while it unstretches or unsquishes is going to be 1/2 kx squared. And that is just because we're looking at an average force, which is 1/2 kx. That force times distance, which is x, is 1/2 kx squared. And so that's how much work the spring can do. And we can think about that in terms of like the work that the spring is actually doing as it pushes on something. That's going to be like this amount of work done by the spring. Or we can think about it as the amount of work the spring could do but hasn't done yet. So if I have a supercart with the spring pushed in, this spring is ready to do work. How much work could it do? Well, it could do 1/2 kx squared work. It's not doing it, but it could. It's not doing it, but it could. And now it did it. So while it's doing the work, this is how we calculate how much work is being done. Before it's done the work, we call it potential energy, because it's potential work that could be done. And that is, we use the letter U to indicate potential energy. We use the subscript S to indicate springs, which is, we don't call it spring potential energy, we call it elastic potential energy. And then that's equal to the amount of work that the spring could do. So it's the same quantity. We kind of think about it two different ways. It's really the same thing. If a spring can do work, it's because it has this much energy. And what I want you to think about there is the connection between energy and work. Energy is the ability to do work. Work is the process of transferring energy. When a spring does work, it's transferring this much energy into whatever it's pushing on. Before it does the work, it has energy. Energy is the ability to do work. This spring, when squished, has energy, and we think about that energy as being stored in the spring. Like, it's there. We can kind of see it in the compression of the spring. We can identify a location for that energy. Now that's not quite right, because we don't really know what energy is, and it's not just one thing that's like here. It's not like located at this spot right here. It's like somehow the whole spring itself, the deformation of this spring, is associated with energy, but it's really easy to see it with a spring. There's energy stored because it's stretched. There's energy stored because it's squished. When it's not stretched or squished, there's no energy stored, right? There's no energy stored in this spring at all right now. So it has no elastic potential energy because X is 0. So with springs, conceptually that idea makes a lot of sense. There's a 0 when it's not squished or stretched. And the energy that's stored is right there to be seen, okay? And so we can think about the work that we were doing yesterday with the PhET simulation in terms of gravity. We can start by thinking about it the same way. So a spring can do work by pushing on something or pulling on something. Well, gravity can do work as well. Gravity is exerting a downward pulling force on everything in the Earth's gravitational field. Doesn't matter whether that stuff is moving or not. It doesn't matter if it's accelerating. The force is the same. Everything in here is experiencing a downward force equal to mass times free fall acceleration. The force of gravity is equal to m times g. If something is falling, that's the force of gravity. If something is at rest, that's the force of gravity. If something is accelerating upward because it's like being pushed by an engine, that's the force of gravity. If something speeds up as it falls, then work must be done. So if we have an object in free fall, we can calculate how much work is done because work is equal to force times distance. So if something is experiencing a downward force of this much and it falls this distance with no other forces acting on it, then the amount of work done to that object is going to be this. It's going to be the force of gravity, mg, times the amount of vertical distance that that object moves, delta h. So if I have a tennis ball and it's 1 meter above the ground and I drop it, then the amount of energy transferred into this tennis ball is m, which I'm guessing is about like 100 grams or 0.1 kilograms. That's a total guess. And the g is 9.8, and h is about a meter, which means I just transferred about 1 joule of energy into this ball by dropping it. The Earth is pulling on it. The gravitational force is pulling down. It moves down 1 meter, and this is the amount of work that was done. Pretty easy to calculate for anything in free fall. Yeah?
So do you transfer the energy, or it was the energy transferred?
Yeah, it's such a good question. You're totally right. And what's interesting, I'm so glad you asked that, because as I said that, I thought, oops, that's not quite right. So yeah, you called it. I said I'm transferring energy into it, but I wasn't.
The energy.
I wasn't doing the work. The Earth's gravitational field was doing the work. So yeah, that's energy was being transferred into the ball, but I didn't do it. Absolutely right. Really, really good. Okay, so if gravity can do work, but it's not doing work, like when I hold this ball up here, gravity isn't doing work, but it could, then it makes sense to think about the work that it could do in terms of potential energy, just like when we were talking about springs. So if we think about gravitational potential energy, it's the amount of work gravity could do on an object before it falls. And if we lift an object up off the ground or off a table, then what we're doing is we're increasing the distance that it could fall. And at that point, we are putting energy into something. If I lift this ball up above the ground, I am transferring energy into this object. Down here, right at the surface of the table, it's not gonna fall if I let go of it. If I lift it up and then I let go, it can have energy transferred into it by the Earth's gravitational field. So that must mean that I gave it energy. How much energy did I give it? Well, I gave it just as much energy as gravity can do work, which means the energy that an object has because of its location in the Earth's gravitational field is this, right here. We use the same variable u for potential energy. It's got a little g now because now we're talking about gravitational potential energy. But there's a couple of things about this that are trickier. A couple of things about this that are not as easy to deal with as with springs. The first is, where is zero? With a spring, we knew that if we stretch it and then let go, it goes back to like this. That's zero. If we squish it and then let go, it goes back to this. This is zero. There's no energy in this spring. With gravitational potential energy, well, if I hold this ball a meter up above this table and then I let go, gravity could do how much work? Well, mg times that distance. But what if I move the ball over here? Now it's twice as high above where it's going to land. I didn't lift it up at all, so I didn't put any more energy into it, but it sure seems like it's got more energy here than it did here. And that's not entirely true. Gravitational potential energy always relates to a change in height. So if something moves from here to here, it will gain kinetic energy if it's in free fall. If something moves from here to the ground, it will gain kinetic energy if it's in free fall. If a sinkhole opens up, if a sinkhole were to open up underneath me right now, don't get your hopes up, I would start to fall and I would gain kinetic energy. We all have gravitational potential energy so long as we are not located at the very center of the planet. That is kind of a tricky thing to calculate. And especially it's tricky to calculate because our weight, mg, this is really only accurate at the surface of the Earth. As we move really far up, or if we were to move really, really far down, closer to the center of the Earth, the rate of free fall isn't 9.8 anymore. So the force from gravity isn't constant, it's just roughly constant at the surface of the Earth. Constant enough that we can use m times 9.8 and call it good. But if we were to drop this tennis ball and it were to fall straight through to the center of the Earth, it would not be experiencing this force the whole time. That force would decrease as it falls. At the very center of the Earth, there would be no force whatsoever. So it gets really complicated. And the idea of saying, well, this ball has this much gravitational potential energy is really tricky. So what we do, there are two ways to look at this, one of which everyone can look at. That first way, the easy way, is to say, look, in any given situation, find the lowest point any object will have. If there's gonna be a sinkhole, if we're gonna deal with a sinkhole, let's figure out how deep it's gonna be and make the bottom of the sinkhole our lowest point. On a roller coaster, the lowest point is, well, it's not the ground necessarily, like the cart may never get to the ground, so that's not the lowest point, but wherever that lowest point is, we'll call that 0. Everything else has gravitational potential energy relative to that point. Things that fall in free fall will speed up, and when they get to that point, we're saying, because we know what like our scenario is, we're just gonna say at that point, it hits the lowest point and stops. If I'm gonna drop this tennis ball, and the furthest it can go is right here, then it has the same gravitational potential energy no matter where it is. If I know it's gonna stop right here, I'm gonna call this 0 and measure my gravitational potential energy relative to that point. If it could go to the ground, then I'm gonna make that 0. And my gravitational potential energy will be measured relative to that point, because that represents the potential kinetic energy of this ball if it fell in free fall all the way to the ground. Okay. The other way, the more complicated way to think about gravitational potential energy is that there is no fixed amount of gravitational potential energy. Things can gain gravitational potential energy by going up. They lose gravitational potential energy by going down. And that can be negative potential. I mean, there's no reason that we can't say that 0 is right here. Things that are above that have positive gravitational potential energy. Things below it have negative gravitational potential energy. It's like the Fahrenheit scale or the Celsius scale in temperature. 0 isn't as cold as you can get. It's just an arbitrary place. If you get colder than that, then you just go into negative. And there's nothing weird about it. If I say that it was -4 degrees in Nome, Alaska last night, you all wouldn't be like, -4! You can't have a negative temperature, but you can. It's just 4 degrees cooler than whatever we called 0. But we're gonna follow the convention that our lowest point is gonna be 0. That will be h equals 0, and all of our changes in height will be relative to that point. So we'll only have positive gravitational potential energies, which will be handy. So that was one of the things that's complicated. The other thing that's complicated is with a spring, remember we can see that energy. You stretch it out, there it is in the spring. You squish it, there it is in the spring. And now it's 0. But what about gravitational potential energy? We generally will want to say that it's in the object, right? Like if I am talking about the gravitational potential energy associated with this tennis ball, I'm going to be like, it has this much gravitational potential energy, or some smaller amount or some larger amount. We want to say that the object has that energy, but it really doesn't. Nothing about the object changes. Think about it this way. If I were to lift this ball a meter up from the table, and then the entire planet were to suddenly vanish, just be moved to another dimension, we're all fine. But the tennis ball stays here. Nothing about the tennis ball has changed at all. Yet it suddenly has no gravitational potential energy because it's not near anything that's pulling on it. So where is the energy? And what I think of, I don't know if other people use this, I don't know. So you may come across this or maybe not, but really where that energy is it's in the field, which is something that's really hard for most people to understand, including me. So what I say instead is, it's in the gravity spring. What's the gravity spring? The gravity spring is a coiled spring like this that's pre-tensioned. So it's stretched out and it goes from the object all the way down to the center of the earth. It's an invisible spring, but it's there. And it's already stretched out. So it's pulling on the object, just like the force of gravity is. If we lift up, then we're stretching that spring out a little bit more. And here's what's key about this. With real springs, if you stretch it out a little bit more, you get more force. With the gravity spring, you don't. It's a constant force. And that sort of makes sense, because if it's already stretched out, like let's say that the gravity spring is, if it were like at its regular resting state, it would be this tall. That's like 0. And then with something on the surface of the earth, it's this tall. And if we lift something up a meter, it's this tall. Not much of a change. It's not really pulling with that much more force when you lift something up a meter. And that's the case with our gravity spring. Our gravity spring is pulling with basically a constant force. So if you lift something 100 meters, or 10 meters, or 3 centimeters, or whatever, the force is basically the same. This analogy will break down actually, and some of you probably figured this out already, because real springs pull with more force when you separate. The gravity spring actually would pull with less force. If we pulled this tens of thousands of meters, what we'd find is that the force is becoming smaller and smaller. But over short distances, it works. We can imagine that it's a spring that's pulling down with a constant amount of force, and pretty much no matter how stretched it is, it's always pulling with the same amount of force. So what's changing is only the distance. It's either this amount, or this amount, or this amount. Just a little bit of distance is changing, and that's it. That's how I think about gravity. So if I lift something up in a gravitational field like the Earth's, what I'm doing is stretching out the gravity spring. The work that I'm doing, force times distance, is the same kind of work that I would be doing if I were squishing or stretching a spring. And when I let go, the spring will do work. How much work? Force, which is constant because it's a gravity spring, times however far down it moves. So that would speed the object up by that amount if it was in free fall. So understanding the gravitational potential energy has to do with the change in relative height is key. Understanding that gravitational potential energy has to do with this conceptual idea of an invisible spring that exerts a constant force on every object. Those things can kind of help you think about what's going on when gravity does work. Let's think about a special condition where gravity is the only force doing work to an object. What does that mean? Well, to do work, you have to exert a force, and that force has to be in the direction of an object's motion, or at least partially in the direction of an object's motion. So there are some cases where it's pretty obvious what's going on, right? If I drop this tennis ball and I just let go, then the only force acting on it as it falls is the force of gravity, and that means gravity is doing work and there's no other forces doing it. If I take the same tennis ball and I lower it, then gravity is doing work, but I'm doing work too, because I'm pushing on it. I can feel myself pushing on this ball. Even as it goes down, my hand is moving down, but I'm still pushing up. That means I'm doing work too. I'm doing what's called negative work, slow down work. Gravity is doing positive work, speed up work. I'm doing negative work, slow down work. And the end result is no net work. This ball has no velocity. Nothing sped it up. So there wasn't any overall work done. So that's not a great thing for making predictions. If we have forces acting on something in the direction that they're moving, or partially in the direction that they're moving, in addition to gravity, we lose the ability to make good predictions about velocity. If I were to tell you that this tennis ball has 7 joules of gravitational potential energy, and I ask you how fast it's going to be going if I let it fall a meter, you can't predict if I tell you that, yeah, my hand is going to be pushing on it too, because maybe it'll be going really slow, or maybe I'll let it go pretty fast. You don't know. You can't predict the velocity when there are multiple forces in the direction of the motion, unless you can quantify them all. But one of the things that's really cool about energy that's not true about kinematics is that we can have forces acting on an object that change their motion without changing their speed. So let's look at that for a second. Let's say that we have a cart, a supercart on a track like this. And we take the track and we tilt it. If I let go, that supercart is gonna move down the ramp. What are the forces acting on the supercart? Well, let's ignore friction for a second. Basically zero. The gravitational force is pulling straight down. The track is at a 90-degree angle to the motion of the cart. The motion of the cart is this way. The only force acting in the direction of the cart's motion is the gravitational force. Not all of it, but part of it. There are no forces acting to slow that cart down. What does the track do? It's pushing on the cart. The track changes its direction. It would go straight down. The track makes it go a different direction, but it doesn't slow it down at all, which seems weird, and we'll see why it works out in just a second. We'll get the same thing with something like this. It's easier to understand with the gewgaw. If we take the gewgaw and we support it by a string like this, and then we let go, it speeds up, right? It's a pendulum, basically. Well, if I were to just let go, down it goes into the pile of soup. But, but I'm not gonna let go. So does that mean it's going slower? Well, no. As it turns out, the speed that this gewgaw has at this point, right here, is exactly the same as the speed it would have right here if I dropped it. The change in height is all that matters. Now what's different is the direction. If I let the gewgaw fall in free fall 10 centimeters, its speed is straight down, the direction is straight down. If I let it fall 10 centimeters when I'm pulling on the string, its velocity is this way, but the magnitude is going to be the same. Same speed here in this direction as here in this direction. And that's because the direction of the force from the string on the gewgaw is never in the direction of its motion. The gewgaw is moving in the direction of my finger. Look at the relationship between the string and my finger. It's always a 90-degree angle. There is force, there is acceleration, but it's not causing a change in speed. It's only causing a change in direction. What that means is that if we can engineer something such that there is nothing slowing an object down, just changing its direction, we can make all sorts of really cool predictions about its velocity by understanding that the work gravity does as it moves lower is going to be equal to its change in kinetic energy. That's the work kinetic energy theorem. If we take this equation right here, the work done by gravity will equal the change in kinetic energy of an object, and rearrange it. Now, I'm making some assumptions here, which primarily that the initial velocity is zero, okay, and that there are no other forces in the direction of the object's motion. But if that's the case, if we have an initial velocity of zero, no other forces in the direction of an object's motion, then its speed, we won't know the direction, but its speed will be equal to the square root of 2 times g times the change in height. It does not matter what else is going on. So think for a second about the skateboard energy ramp thing that we saw. We had the skateboarder going up and down and up and down and up and down. It was really hard to figure out how fast she was going by using kinematics. But if we think about the fact that at any one time, the track, the ramp that she was on, was always at a 90-degree angle to her motion. The force from that ramp was always normal to her motion, perpendicular. That means the ramp didn't speed her up or slow her down at all. It just changed the direction of her motion, which means we can figure out how her kinetic energy is going to change just by looking at her change in height. That's all we need to know. And her mass. We need to know her mass too, but we don't need to know We don't, in the case of predicting her velocity, the mass drops out anyway, so we don't really even need to know that to figure out what her change in velocity is going to be. And that's pretty slick. That's really powerful, to be able to look at an object and say, well, it moved 2 meters down, its kinetic energy must have changed by this amount, so its speed must have increased by this amount. That will be true if there are no forces in the direction of an object's motion, and the only force acting on it is the force of gravity. So what I'm going to ask you all to do is kind of test that out. And there's a bunch of different ways you can do it, but the key is that you have to make sure that you aren't putting forces on the object that will cause it to speed up or slow down. So you can be experiencing a bunch of different forces, just like my gewgaw is experiencing 2 forces as it's moving, but only one of those forces is doing work. The force of gravity is doing work. If we have a ramp and we tilt it, the force of gravity is the only force doing work. The ramp is always pushing perpendicular to the object's motion. So the force in the direction of the object's displacement is 0. And some of the more brilliant students in the first period class recognized that if you're careful and you take the big whiteboards, you can create curved ramps with those in either direction, right? Like you could take that big whiteboard and make a ramp that's curved like this, or you can make a ramp that's curved like this. It's trickier probably to make something along these lines, but I mean, if you're careful and you don't snap it, you could probably pull that off. And so what your goal is to try to engineer a situation in which you can predict what an object's velocity is going to be as it moves through a relatively complex space. So what I'm going to ask is a couple of things. One is, you can't just drop something, okay? The second is, however you do this, you need to make sure that there aren't other forces in the direction of the object's motion, or your predictions are going to just be wrong. The third thing is, I don't want you to use kinematics. So ideally, you wouldn't just use a straight ramp. If you do use a straight ramp, though, what you'll see is that kinematics allows us to make a really accurate prediction if an object is either in free fall, if acceleration is 9.8 meters per second squared, and initial velocity is 0, then this ends up being the same equation I just showed you. If an object is on a straight ramp with a constant force, then the acceleration is going to be g sine theta. So instead of g, it would be g sine. It's pretty easy to use kinematics. If we have straight ramps with constant acceleration, we can use kinematics, so don't. I want you to use conservation of energy. You can either use a straight ramp and use conservation of energy, or use gravitational potential energy, or you can do something more complex where you just wouldn't be able to have a single angle. It's not in free fall, it's not a constant angle, so you wouldn't be able to make your measurements and calculations like that. The last thing that I want you to think about is this piece here, which is what we're looking at is the object's instantaneous velocity at the end of its motion. That is something that's a little bit trickier to measure than, say, its average velocity, or even if you use tracker, its initial velocity. And I'm going to make it a little bit more complicated by having one of the rules be, you cannot use an object that has a built-in way to measure its own speed. So you can't use the supercarts, nor could you use like a motion sensor. If you want to use tracker, you can, but probably what you're going to find is it's not as easy as you think. There's a relatively easy way to figure out the object's speed at the end of its motion in a variety of different ways, but I don't want you to use something that measures its own speed, okay? All right, so that is that. Does anybody have any questions before you get started? Challenge yourself with this. If you know exactly what you would do and how you would do it with a straight ramp, then don't do it with a straight ramp. Push yourselves a little bit. There's an assignment that's posted to Canvas, and if you look at that assignment, you'll see that a big part of it is your design. And what I want you to think about here, if you're in AP Physics, is that this is a huge part of the exam. They ask you to tell me what you would do. How would you make these measurements? What kind of instruments would you use? How would you record your data, and how would you evaluate it? So all of this stuff in part A is really critical for those of you in AP Physics. If you need to take a break, now's a great time, and you have the rest of the class period to work on this and probably longer, and I'll be here to offer you any help. Don't slip in the soup.